Good afternoon or good morning, depending on where you're located, and welcome to the Climate Seminar Series. Today we'll be talking about winter teleconnections, Part 1. Our presenter today is Steve Baxter. Steve has just taken a position in Climate Services Branch. It was officially announced today. Prior to that, he was with the Winter Weather Services Program Manager, and before that, you might recognize his name from working at the Climate Prediction Center, where he was a forecaster working at various time scales and also working in applied research to operations. He's been engaged in some interesting projects related to statistical methods and extended range forecasting, the probabilistic hazards, seasonal forecast consolidation, week to 3 to 4 forecast development, and teleconnections at subseasonal to seasonal time scales as well. Steve got his undergrad degree at Millersville and his advanced degrees at the University of Maryland. So Steve, let me be the first to welcome you publicly to Climate Services Branch, and let folks know that if you have questions for Steve during the presentation, you can put them in the chat box and we'll address those at the end of the presentation. And this will be recorded for folks to view later. And with that, I'll pass it on to you, Steve.
Great, Ray, thank you for that very nice introduction. I'm really happy to be back in climate space, working at the Climate Services Branch now after pretty long time, like you said, at CPC, and then of course at the winter program at headquarters. So really happy to be back here in climate. I'm really excited, very fitting that my first week in that position, I get to do this little webinar, part 1 on winter teleconnections, something I've been really interested in my whole academic and professional career. It's been a long-standing interest of mine, just as a person who loved weather and climate from a pretty young age. Teleconnections have been part of that interest. And so I'm really excited to share that with you today. And I hope that you I hope that I motivate you a little bit, and I hope that you are ask questions very freely. Jenna will read those questions as we go at the end of the presentation, but I do encourage you to ask a lot of questions, and I'm looking forward to them as well. So let's go ahead and get started here. So just a quick outline here, talk about why we care about climate variability from a weather perspective. We're in the National Weather Service, we like weather. Why do we care about climate variability? And I'll do an introduction to teleconnections. And then, like the title suggests, this is winter teleconnections. So why do we focus on winter? What happens in summer? And what's different about that? And I'll talk a little bit about that. And talk about how we identify teleconnections. So I'll present a couple of methods in brief, just to kind of whet your appetite for kind of the diverse way in which we can understand and identify teleconnections in our various data sets. And then I'll kind of go through the meat and potatoes of today's portion, which is to kind of overview the teleconnections that we see, that are internal to the extratropics. So these are some of those teleconnections that you'll know likely by name, like the North Atlantic Oscillation or the Pacific North America pattern. I'll introduce maybe perhaps a lesser known pattern called the North Pacific Oscillation or West Pacific pattern. We'll talk a little bit about that as well. And then finally, we'll end on basically an understanding of what causes these teleconnection patterns to favor one phase over another, which is to suggest that there might be some sources of prediction skill. Where do those come from? And the last thing I'll talk about in our part 1 here today, and part 2 will be next month, so looking forward to that as well, is a kind of a cautionary tale for how we have to be careful when we apply kind of index-based assessments of climate variability. And so there's kind of a cautionary tale with the Pacific Decadal Oscillation, or the PDO, that I'll step through because I think it's really a good case study for how we can use teleconnections, but how sometimes we need to be careful not to misuse teleconnections when we're doing climate analysis, trying to understand climate attribution through the lens of teleconnection analysis. And then finally, I will do a little preview of our part 2 that's coming up next month, which I think will be really exciting before we take questions. So as we're pretty familiar, we have long waves and short waves that we see in our mid-level analysis. We like to look at 500 millibars a lot here. And so here's an example that I pulled last week when I was putting this together. This is a 384-hour forecast. This is way out there. just our deterministic GFS taken from tropical tidbits here. What's kind of neat about this, so 384 hours, of course, we don't expect any weather prediction skill at that timeline, at that time lead. And so with a single snapshot of the atmosphere at 16 days in the future, we certainly don't expect it to have any prediction skill. However, it's a physically plausible representation of atmospheric variability. So for the purpose of identifying things like long waves and short waves, you can kind of see those features. Kind of interestingly here in this atmospheric map that I'm showing, you can kind of actually see kind of a wave 5 pattern. And so you have 1, 2, 3, 4, 5, roughly, long waves as you go around the hemisphere. But what's interesting is, of course, embedded within those, you see short waves, and you see little cutoff lows here and there. You see individual, what essentially would correspond to vorticity maxima that are pivoting through the long waves. And so these, we think of kind of teleconnection analysis as trying to smooth over a lot of the shortwave variations and focus on the lower frequency or the standing patterns of variability. So when we look at that, we might look at something like this is from an ensemble mean for a 5-day average. And in this framework, you can see it's a lot harder to identify short waves when you start averaging over longer periods of time. And then taking this even farther, if we were to do weekly, monthly, or even seasonal averages, that's really where the climate footprint becomes more obvious. And it's in that context that we often conduct that teleconnection analysis. So why do we care about climate? So these are really 4 kind of rhetorical questions that I answer. So not really rhetorical questions, but the first is that climate variability, while we can diagnose it from statistical analysis, it's not just a statistical residual or kind of an artifact of daily weather. So it does have are real climate variability signals that are really important to understanding the climate context in which weather events are occurring. The other is that are there distinct and predictable low frequency variations that are longer than our synoptic timescale? So once we get beyond our 7 to 10 day forecast period, are there things that are distinct and predictable? And the answer is yes. That doesn't mean everything is predictable. Even things that we can identify as real signals from a climate variability perspective, that doesn't excuse me, necessarily mean it was predictable. But there are in fact predictable changes. We'll discuss those a little bit this seminar, but especially in our part 2, which will be a little bit more applications driven. And then are these low frequency changes in the base state, are these large enough to affect daily weather? And the answer here is really an emphatic yes. We really need to be, it's important to understand that when we're in these base climate states, and we often think of them as phases of a teleconnection pattern in a positive NAO, for instance, or a negative NAO. We are more likely to see certain types of weather and certain types of even extreme weather. Now, those shifts, if you will, in the likelihood of those events occurring aren't necessarily huge in absolute terms, but they can be quite large in relative terms. It can be important to, again, understanding the context in which certain types of weather are more or less likely. And then, is their impact large enough to be seen in every weather event? Or is it only obvious when considered over a number of events? And then the answer here is it depends. So it is obvious when you consider over a number of events. We really emphasize the aggregation of data in space and time to construct climatologies and look at the variation of climate over time. Yes, it's obvious in that sense, but certain weather events can very much have a very significant portion of them that are attributable to a climate-based state that made their occurrence much more likely, to the point that we could say a very large percentage or a sizable percentage of a given weather event can even be attributable to the impact from lower frequency climate variability. All right, so with that little bit of background, jumping into teleconnections. So the definition of a teleconnection is a phase relationship between geographically distant points. So this figure here is really interesting. This is from the 1932 Walker and Bliss paper. So Walker identified a lot of these teleconnections. And one of them, of course, being the North Atlantic Oscillation, which is what we're looking at here. Is this kind of an old map here of the relationship between the North Atlantic Oscillation, which in this context would have been identified as a pressure dipole between Iceland and the Azores in that vicinity, with surface pressure, surface temperature, and rainfall during December through February, which is our meteorological winter. So there's other teleconnections as well. So and we'll talk about how we identify these. But one of the ways that you can do it is by looking for these anti-correlated points. And so if you take a point near Iceland, for instance, and you look for the point anywhere in the domain you're looking, so if you're looking in the northern hemisphere, for instance, and you look for the grid point whose, say, monthly pressure, sea level pressure, is most negatively correlated with the point in question, say near Iceland, you'll find something that's in the vicinity of the Azores in the North Central Atlantic. And you can do that all over the globe. What you can do is you can find general areas that are better teleconnected to certain regions than others. And so that whole framework helps us to get our bearings to where we're looking for these phase relationships. Another great example of a phase relationship that's in the tropics is the southern oscillation. So when sea level pressure is anomalously high in the West Pacific, it tends to have the opposite phase in the East Pacific, and that's of course associated with the El Nino phenomenon. And so teleconnections in that framework operate in the tropics, they can operate in extratropics. You can do little exercises where you can look for at any given grid point where you are. Like for example, here in Silver Spring, you can look for a grid point in any field, temperature field or pressure field or height field, that is most negatively correlated with monthly data at our given location. So if you were to do that, for instance, in temperature, you'd find that a grid point, say, near NWS headquarters in Silver Spring, is best teleconnected in temperature with northern Alaska in the wintertime. And so that strongest phase relationship exists between, say, the mid-Atlantic, roughly, and northwest Canada and Alaska. So as we follow synoptic variations of weather, it's not surprising that we have these really big ridge patterns that develop over northwestern North America and over Alaska that tends to be associated with a really high amplitude discharge of Arctic air down toward the CONUS, and especially the central and eastern CONUS. And so that's another area in which teleconnections can be manifest, just in general. So before we get into a little bit more detail of the methods in brief, think about why we focus on winter. So during winter, horizontal temperature gradients are the strongest. This drives our synoptic variability. And this is in fact organized and characterized on climate timescales by these leading teleconnection patterns. And so what that means is that during the winter, we need fewer of these organized teleconnection patterns to explain the variance that we observe in the winter. And in the summertime, we need more patterns because the synoptic variability, the spatial distribution of anomalies is much more chaotic and less organized than it is in the winter. And so for that reason, our discussion of teleconnection patterns tends to focus on the winter. While they are defined in all seasons, I'll show an example here coming up in a second, their utility is best understood in our ability to reconstruct climate variability and associated weather events in that climate context is best applied in the cold season when we have these horizontal temperature gradients that drive the important synoptic variability that we're attempting to categorize. And comparing winter and summer teleconnections is not trivial, which I'll show an example here in a second. But what I mean by that is when our understanding of something like the North Atlantic Oscillation, for instance, is very much driven by winter variability. In fact, it's during the winter when variability is strongest. So if you look at something in the winter time, you'll find that the fundamental nature of variability in the North Atlantic in summertime is just a bit different than it is in the winter. And so categorizing variability as being related to a summertime NAO, you can certainly do it, and we do it, but it's not super straightforward. There's no textbook necessarily way of doing that. So I'll show an example here. This is an analysis of the winter time, or the DJF pattern on the left, and on the right here is the summer JJA pattern for the NAO. And so in this example, the NAO on the left in the wintertime, this little number up here, 16.8%, is the percentage of explained variance in the height field for which this analysis is conducted Now, if you compare it to the summertime, the percentage of explained variance of a similar pattern, which has a similar spatial footprint with the general centers of action, it's much lower. It's about a third. And again, it's pointing to this nature of the climate system being more chaotic and needing more and more patterns, these smaller scale patterns, to explain the same amount of variability that we observe. Likewise, if you go to the bottom panel, this is the footprint in the temperature field. You can see it tends to be a little bit weaker and less canonical in the sense that we don't have this kind of north-south dipole as clearly manifest in the summertime as we do the wintertime. But the other thing is that you can take this and you can say, well, maybe we define the NAO, or teleconnectivity in the North Atlantic in the summertime might look fundamentally different than it does in the wintertime. And so actually this pattern that you can see here is actually the 6th leading pattern in the Northern Hemisphere. It's not even the most important pattern in the North Atlantic in the summertime in this particular analysis. So the point there is that we can't always draw one-to-one comparisons between the winter and the summer particularly easily. So as we go through, I'll show you examples of the current operational teleconnection monitoring suite at CPC, and you'll see how our ability to really use these to communicate understanding of climate, provide climate context for weather events, really starts to break down in the summertime, kind of reiterating why we're focusing here on the wintertime variability associated with teleconnections. So methods, briefly, there's multiple methods, and this is just kind of motivational. But I'll focus just quickly on two. The first I alluded to before, which are these kind of seminal teleconnectivity maps. These are based on point-to-point correlation, where you identify the grid point of the domain with the highest amplitude negative correlation. And you do that at each point, and then you identify local maxima. And these are identifying the centers of action of various teleconnection patterns. So I'll show an example on the next slide. And then you can construct an index, a time series, by utilizing the time series of the standardized anomalies at each grid point. So I'll show an example of that on the next slide. The other method, and the one that's used more often overall now, is using some variation of empirical orthogonal function analysis. You'll also see this called principal component analysis, PCA. This is a linear algebra method to identify recurring patterns of variability in a data set, and they're sorted by explained variance. This has the added feature of yielding time series that are uncorrelated. So in that framework, it means that you could have disparate forcing mechanisms that are totally independent that lead to these patterns that are that in space could overlap in variance of this analysis, but that in time we're still uncorrelated. And so that's nice, so you can reconstruct linearly. You can just add up the contributions from each of these patterns to reconstruct the state of the climate at any given time, or reconstruct the contribution of those patterns to some observed weather event. So here's an example of a teleconnectivity map. So this is identifying two key patterns here. So this is that teleconnectivity map I mentioned, that method I went through at 500 millibars. And basically, and this is from 1949 to 2009. But what you see here are these centers of action. And so generally speaking, what you're seeing in the North Pacific and the North Atlantic are the two greatest best teleconnected areas in the North Atlantic and North Pacific, respectively. And then between the North Pacific and Northwestern North America, you see a third kind of dipole. And so these three centers of action over the Pacific into North America domain constitute the three prominent centers of this analysis of the Pacific North American pattern, of the PNA. And then this pattern of the Atlantic is, of course, more closely associated with the North Atlantic oscillation. One thing that's interesting is that typically the Pacific North American pattern is also associated with a center of action over the southeastern United States, and that's less prominent in this analysis. And so some of these are in fact sensitive to the type of analysis you should perform. But this is just kind of an example of the type of analysis you can do to identify teleconnections. The seminal analysis that was done that informs the current suite of CPC teleconnection monitoring products is the Barnson-Livesey analysis in 1987. And this analysis shows the whole suite of standing patterns in the atmosphere that are in fact the dominant teleconnections that impact North America. And these explain together almost all of the wintertime, monthly, and seasonal variance over this domain. And what's important, I'll get into a discussion briefly about this a little bit later, but the four physical modes, or the four things that really drive climate variability: long-term trends, ENSO, tropical intraseasonal convection, so something like the Van Julian oscillation, and extratropical variability, or internal variability extratropics. Those four physical modes often manifest themselves as one or more of these teleconnection patterns. It's important, and I'll come back to this when we talk about this kind of PDO cautionary tale. That's that the relationship between patterns and physical modes is not one-to-one. And so I suggest this is to the extent that this is true, is a weakness of the analysis paradigm. We want to seek out an analysis framework where the teleconnection patterns we identified and underlying physical patterns or physical modes are closer to one-to-one. And so to that extent, that's where some research and ongoing work in teleconnection analysis is to understand the physical modes, the physical reality that's underpinning these patterns that we observe in our various analysis techniques. And so here's a breakdown of these patterns in brief. So the top three are extratropical patterns predominantly, in that they tend to be strongly internal to the extratropics in their forcing. They occur during all seasons, but they're much, much stronger in the winter, and they explain a lot more variability in terms of surface climate in the winter, which is why we focus on the winter variability. In the bottom row here, we have the El Nino Southern Oscillation pattern, which you'll also see in some cases as the tropical Northern Hemisphere pattern, the TNH pattern. And this is generally, to the extent that it's ENSO related, is forced by the tropics and by El Nino. Generally, it's the stronger the ENSO pattern, the more you'll see this type of teleconnection pattern manifest. What's interesting is that another aspect of understanding teleconnections and our work to better understand the role of ENSO in generating climate anomalies in the mid-latitudes is the difference between El Nino and La Nina. And there was a time when it was thought that only El Ninos, this was some time ago, that only El Nino had a really strong extratropical footprint. We knew that La Nina does as well, but they're not perfectly linear. And that's one of the areas we're seeing here is this 1987 analysis very much identified this TNH pattern that was really robust during moderate to strong El Nino years, but that the opposite phases weren't as closely connected to moderate to strong La Nina years. One of the things that I would posit now is that that's a feature of having an analysis framework where there's multiple physical modes that are contributing to these different patterns at different time scales. So it can make it challenging to disentangle some of these things. And ENSO tends to have a much stronger footprint in the cold season in the mid-latitudes because of the ability for tropical interaction to occur on that interface where you have the jet stream. You have the ability to generate a wave source that can communicate tropical convection into the mid-latitudes. And so again, that's another important reason why we focus on the wintertime. So this is from that original 1987 analysis that shows some of the key patterns of variability here: the North Atlantic Oscillation, the Pacific North America pattern, the NAO and the PNA respectively. And then the bottom two are the West Pacific Oscillation, WPO, or the West Pacific pattern you might see. And then you have the tropical Northern Hemisphere pattern, or this kind of ENSO-related pattern you see here in the lower right. Updated analysis that I contributed to back in 2015 has similar patterns, but has a slightly different analysis, framework that was trying to better capture and separate the internal variability of the extratropics from the El Nino Southern Oscillation footprint. And in that framework, we have the North Atlantic Oscillation, the Pacific North America pattern. You have this ENSO TNH pattern it's very grounded in this ENSO-related dipole over the East Pacific. And then you have the North Pacific Oscillation, West Pacific pattern, which is a larger scale pattern that tends to capture a good chunk of the North Pacific Oscillation, as well as the West Pacific pattern that is associated with that kind of original Marsden-Livesey analysis over the West Pacific. So digging into some of these in a little bit more detail, the NAO, this is a big one. This is the most important. Extratropical mode is also a pattern. So this is very real. It appears in all of our data sets, modeling analysis alike. We say it's the most important Northern Hemisphere extratropical mode in general. Is it the most important for North America? However, that depends. To some extent, that's it's kind of a southeast coast perspective. If you move up out of the southeast towards the mid-Atlantic, the northeast, or large swaths of the central western part of the U.S., then no, the NAO is not the most important northern hemisphere. It's not the most important teleconnection pattern, although it is always the most prominent northern hemisphere pattern. And so for northern and western Europe, for instance, it's by far the most dominant pattern. So it's important all year round, but again, of course, it's much stronger in the winter time. So this represents a zonal and blocked extratropical North Atlantic in its positive and negative polarities, respectively. So in the positive NAO, you have a very fast and a very an enhanced jet stream, whereas in the negative NAO, you are more likely to have blocking patterns, right? So you reverse the climatological Icelandic low, Azores high framework, you weaken or reverse that, and then you get a blocked flow over the North Atlantic. And this is where the relationship between the NAO and Eastern U.S. weather and climate come in, because what we've observed is that because of that tendency of negative NAOs to be associated with blocking the North Atlantic, this has an impact on the upstream storm track over Eastern North America. And so it's not surprising in that context then that a negative NAO is associated with a storm track that's much more conducive to, for instance, East Coast winter storms than the opposite, more zonally enhanced framework of the positive NAO. So an early definition, like I mentioned before, was a difference in sea level pressure anomalies between the Azores and Iceland. This is kind of a center of action analysis. The current CPC framework defines it using what's called PCA or EOF analysis. That's a little bit more rigorous and allows it to be better differentiated in time from other patterns that are also explaining a lot of variability over the Northern Hemisphere. So this is a figure that you'll find on CPC's webpage. I'll link to the current CPC operational webpage here later toward the end of the presentation. And that's where these come from. So from winter to summer, the NAO weakens quite dramatically, and you'll see its meridional scale decreases. So by the time you get to July, okay, you have a pattern similar to what I showed very early in the presentation. The January and July panels are very comparable there. You see this quite differently. I do want to note, like I said before, that the definition of teleconnections between the warm and cold seasons is debatable. So we can call it the NAO because it's spatially similar to the pattern that we observed in January. But for instance, in January, it's associated with a meridional shift in the storm track. So, but in July, that's not the case. Where the climatological storm track is different, it's actually more associated with an extension or retraction of the jet stream, for instance. And so in that framework, it's just reiterating these differences between summer and winter that make summer teleconnection analysis a little bit murkier and a little harder to apply, especially when compared to their wintertime counterparts that are very well traveled, defined, and useful for understanding the current state of the climate, multiple time scales, and their potential impacts on weather. So when we look at this in surface temperature, you see the same framework, right? So in wintertime, a very robust temperature footprint weakens outside of winter dramatically. And of course, like I said, over the eastern U.S., the strongest footprint is over the southeastern U.S. As you get outside the southeastern U.S., it's actually not very strong. And of course, it's known for this big footprint from Africa up into to northwestern Europe, over Africa and Eurasia, where it actually explains the most variability in the wintertime. Precipitation is interesting because the precipitation footprint in general is weak over the U.S., even though I did mention this tendency for winter storms to be associated with the negative NAO because of the blocked nature of flow over the North Atlantic that has an impact on the north-south distribution of the storm track. So that is interesting that we don't actually see in the mean a more or less precip per se, but on a storm-by-storm basis, we tend to see a winter storm framework that's more favorable to the negative NAO pattern. Now, contrast that with parts of Europe, you see a very dramatic precipitation footprint. And again, this is associated with that north-south shift in the storm track over the North Atlantic associated with the NAO. So the NAO is not sufficient to explain the vast majority of precipitation variability that we observe over the U.S. So the NAO, in terms of predictability, this is a really important topic because there's been a lot of discussion about the ability to predict the NAO, not just out in our numerical weather prediction time periods, but beyond that. And so I'll dig in a little bit to this a little bit more in our next webinar next month. But in general, it's somewhat like a red noise time series, and it may be some modest predictability for wintertime from very long period changes, potentially like Atlantic multi-decadal variability, itself a debated topic in the climate community, but there was at one point thought to be fairly dramatic decadal variability potentially with the NAO. That's not as prominent in the most recent literature in terms, especially from a predictability perspective. And then predictability of intraseasonal and interannual timescales is generally limited beyond numerical weather prediction. So our ensemble systems, our best ensemble systems can predict the North Atlantic oscillation with some skill, but it's quite limited beyond numerical weather prediction time periods. That being said, there has been some potential seasonal predictability identified from other boundary conditions such as the stratosphere, Arctic sea ice, and sea surface temperatures. And so those boundary conditions to the climate system are external to the extratropical atmosphere itself might give some modest predictability. This is a pretty nascent climate in climate prediction science. And subseasonal predictability may also be related to tropical convection on intraseasonal timescales. So like the Madden-Julian oscillation, MJO, that can play a role in shifting the distribution of the NAO towards a negative or a positive phase on subseasonal timescale. So in that weeks 2 to 4 time period, you might gain some predictability there from that as well. Now, we can't have a discussion about the NAO without discussing the Arctic oscillation of the AO, which is very similar, and they're correlated about 90%, but this is a slightly different framework. And like I said before, a lot of teleconnection analysis can be tweaked or you can look at things from slightly different angles by tweaking your analysis framework. And so this is one such way. In the late 90s, there was a paper that identified the Arctic oscillation, which looked at an all-season EOF analysis. This is that principal component analysis. So it's all season, and they came up with this pattern, Arctic oscillation, that you also see referred to as a northern hemisphere annular mode because it looks like an annulus with a donut. And it's even more clearly annular if you look at the Antarctic oscillation, where the climatology, because of the continental structure in the southern hemisphere, is very much annulus. Let me go to the next slide here. Sorry. So the AO, very similar to NAO, you'll often see more closely associated with discussions of the stratospheric polar vortex and the ability of the stratosphere to influence tropospheric variability. And so this is, again, I'll touch on this in our next webinar a little bit. And then even beyond that, in November, there's going to be a whole climate service webinar dedicated to the ability of the stratosphere to potentially influence and provide prediction skill and have impacts on the troposphere at some lead. So in this framework, looking at AO, sometimes you'll see something like maybe 6 to 8 weeks of potential prediction skill following extremes in the stratospheric AO component, associated often with stratospheric warmings. A couple of papers here that if you're interested in following up on, you'll see some more discussion here of this potential prediction skill. The difference between the AO and the NAO, this is kind of an interesting, kind of a little bit of an esoteric debate, but an interesting one that occurs in the climate science field. But the difference is generally an artifact of the analysis scheme, which another way of saying that is that it's really hard. I haven't seen this done, is to get separate NAO and AO patterns in the same analysis. It's just a function of your analysis framework. And so no matter how you slice it, you tend to get very highly correlated data sets, time series on the order of like 0.9. But this is something that's interesting. You'll see debated a little bit. And when you hear discussion of AO and NAO, we're generally talking about the same general phenomenon. The AO is kind of taking a more holistic hemispheric approach to the whole problem. The NAO is more of a regional manifestation of the AO and emphasizing the variance that explains over the North Atlantic sector. But again, that's just an analysis. That's just based on the analysis framework. It's not taking it back a little bit to our discussion, which we'll follow up on in a bit, between physical modes versus patterns that we see in an analysis. It's hard to discuss there being a physical mode difference between the NAO and the AO. Very similar in that framework. Moving on to the next slide here, the PNA. So we'll transition a little bit from the NAO into the PNA. So it's another one you'll see a lot. The PNA, again, dominant during the cold season, during January, weaker, and even over North America, very low footprint at all as you head into the summertime. Of course, you see that very dramatically in the temperature footprint as well. And so here, even though it always explains less variance hemispherically than the NAO, you can see its temperature footprint over North America is very robust, very important in terms of explaining temperature variance from week to week, from month to month, and even season to season over North America. So that's a very important pattern here. Also, the precipitation footprint is very dramatic. A big hallmark of the precipitation footprint from the Pacific North America pattern is the tendency to create this dipoling over the eastern conus, where you tend to have meridional shifts in the storm track that really clearly show up here in the PNA, where you tend to have storm track shifted south over eastern North America. In the opposite phase, the negative phase, you have that northward shifted storm track with that kind of wet Tennessee, Ohio Valley, Great Lakes footprint. Other than that, it's more modest over the west until you get over the North Pacific, where that clear extension associated with that clear north-south shift in the storm track is noted here over the Northeast and North Central Pacific. So the last pattern here we'll talk about in detail is this West Pacific oscillation, or you'll also see this will also be termed the MPO-WP pattern that you'll see here. This map here shows it more in its West Pacific pattern manifestation. And in this particular analysis framework, the downstream footprint over North America is a bit muted. So from this analysis framework that we published in an encyclopedia article back in 2015, which can take a slightly different analysis framework. You can see that MPOWP is really the dominant kind of warm or cold continent pattern that is associated with upstream circulation anomalies over the North Pacific. And so when you have these ridging patterns, and if I go back for a second go back to this one, because it'll explain that a little bit better. On this one here, so this bottom left panel here is that associated with MPOWP pattern. And so in the positive phase, where you have these strong negative height anomalies centered over, say, the Bering Strait, you have a lot of Pacific origin kind of maritime air that floods the continent. The opposite phase, the negative phase, where you have anomalous ridging and a tendency toward blocking over the North Pacific and the Bering Strait, that tends to generate a lot of cross-polar flow and the generation of negative temperature anomalies over much of North America. And so again, it's an important pattern in a slightly different framework that from a different analysis perspective, that variability that you see in this map here that's coming up, this middle panel here, that'll often kind of get pushed into a different pattern, like, for instance, the West Pacific pattern. You might hear something called the East Pacific pattern. And so some of this is just trying to construct an analysis framework that's just useful for reconstructing different climate anomalies. And hopefully, like I said early, trying to align these teleconnection patterns with underlying physical mechanisms or physical modes, as we'll hear termed. One of the things I wanted to show here now is, as a resource here, how you would access these patterns and the predictions in the short term, the weather timescale predictions here. So this is the current CPC Teleconnections webpage on the left, and there's a link there at the top. This page here shows the current GFS ensemble mean outlooks for the PNA and the NAO, and then as well as these annular mode constituents, the AO and the AAO, which is the Antarctic equivalent. What I wanted to point out here is if you click on monthly teleconnection indices, that takes you over to this really interesting information page that has all these patterns, discussion of these patterns, and understanding how they're calculated in more detail, monthly the archive of all the indices back to 1950 for any analysis or that you might be interested in taking a look at. So I wanted to provide that here as an important resource that you can use as you're exploring some more topics here. So talking quickly about physical modes here, physical phenomena that dominate the Pacific North America region. So one is climate change. So in anytime analysis now, you also have to account for long-term trends. That's especially important depending on the variable of choice that you're using. I've done a lot of teleconnection analysis in the upper troposphere, and in the upper troposphere you have a lot better tropical extratropical interactions, and so identifying El Nino, for instance, in the extratropical height field is ideal there. However, you also have much stronger long-term trends because of the overall warming of the troposphere. That's often you'll see that manifest, right, hydrostatically. You'll see it manifest as a general increase in upper level height fields with time. So we have to account for that. So that shows up a lot. ENSO is really important. It's our most predictable extratropical. It's our biggest single source of extratropical prediction skill outside of long-term trends over North America, and that's ENSO. And so it's very important there. Natural internal variability. So this is the tendency of the atmosphere to organize around these patterns of variability. And so this includes things like the North Atlantic Oscillation, to a large extent the West Pacific or the North Pacific Oscillation, West Pacific pattern, the PNA, which does historically have a component related to tropical variability. In a depending on the analysis framework, we can actually separate them, and you'll see that, and we find that the PNA itself is nonetheless also does have an important natural internal variability component to it. And lastly, the ability of the tropical intraseasonal convective variability to affect the extratropics is important. And so the most important pattern there, most important oscillation there, a mode that we'll talk about in more detail next month, is the NJO, which I talked about a little bit already. So this is kind of lining up some of these patterns. So in the Baxter and Nagam encyclopedia article, ENSO kind of closely lines up with this ENSO-TNH pattern that I showed earlier. The MJO you will see manifest as either phase of the PNA, NAO, or MPO, and then depending on your analysis framework, so we do an analysis framework that emphasizes week-to-week variability and emphasizes the tropical-extratropical interaction component, we actually can separate a unique MJO response pattern. And that was part of an effort to kind of align those analysis techniques with physical modes like the MJO, for instance. Global change is tricky because that can be, like I said, aliased into these ENSO patterns, because what happens is El Nino is associated with large-scale warming of the tropics, at least, and so you see these height increases over the tropics, but so is global change and global warming. So you see that there also, and so there can be, so in non-detrended analysis, you can have aliasing problems there. And then extratropical NAO, AO type variability is manifest by all the patterns that we see here. NAO, PNA, MPO, WP, those all have a very strong internal variability component to them. I was just kind of comparing that to the legacy work of Barnes and Livesey. In this framework, typically you would have this distinction between the TNH and the PNA patterns. So in this framework, the PNA would be associated with La Nina, or a weak NA or a weak El Nino, and then a strong or moderate El Nino would be associated with this TNH pattern. MJO would all be kind of wrapped up in a PNA, WPO framework, potentially an NAO component there as well. Not as much in terms of global change, one because of the time period of the analysis, but also the variable that was used in terms at the time, 700 millibars has less of a global change trend component to it than variables higher up in the troposphere. And of course, the same internal modes are manifest in those internal extratropical patterns of variability. So where we have predictable U.S. weather climate links are long-term trend, El Nino, La Nina, which we talked about, very important, our single biggest source of interannual prediction skill. Subseasonal extratropical variability, especially MJO. This can be manifest in terms of precipitation, tendency for cold air outbreaks or lack thereof, tropical cyclone activity. And then the last one here I've added here is stratosphere and air sea ice interaction. This is where a lot of ongoing work is happening to understand whether the role of the stratosphere in serving as another predictable U.S. weather climate link. So for instance, to anomalously strong stratospheric vortices or weak stratospheric vortices in the context of, say, southern stratospheric warming, do those have predictable consequences for U.S. temperature footprints, for instance? There's a lot of good work going on there to understand that and to be able to apply that. Likewise, air-sea ice interaction, anomalous sea surface temperature gradients in the extratropics, which we'll talk about here real quick in a second. Sea ice, where we have reduced or anomalously enhanced sea ice, does that serve as a boundary condition that can give us prediction skill at subseasonal to seasonal timescales? And so that's an ongoing area of research, but a potential area of predictable U.S. weather climate linkage. All right, so I'm going to end here mostly on this kind of cautionary tale. So I'm going to use the PDO as a great example. As a lot of this work and this training has its roots in analysis and work that was done by many people, including Matt Newman recently, who's done a lot of work on the PDO. And so the Pacific Decadal Oscillation is defined, it's kind of definitional, as this leading pattern of monthly mean North Pacific Ocean sea surface temperatures. And so this is using that type of EOF analysis that I identified before that we use a lot in teleconnection frameworks. And we often think, we used to anyway, think of PDO teleconnections to tropical SSTs, sea surface temperatures, or North American temperature precipitation by looking at correlations between that index and surface temperature precipitation. When this was identified, it was a big deal because it was initially related to salmon production and was thought to maybe be independent events, so another type of pattern of variability that we can address. But the reality is that it's really not, in that the PDO depends a lot on ENSO. So ENSO itself helps predict the PDO because of El Nino's extratropical footprint. And then there's a low frequency component that comes from some other patterns of variability. So in this example here, when you take the PDO and you remove the influence of long-term trends and ENSO, you don't have any connection to the tropics, and you're likely left with internal variability. And the reason that's important is because what it's showing us is that the PDO is a great example of a very real pattern, okay, but one in which there are many physical modes that contribute to it. And so, for instance, in the extratropical North Pacific, SST variability is dominantly driven by these extratropical teleconnection patterns, okay? And so you have all of these different physical modes that are contributing to these teleconnection patterns, that are driving these teleconnection patterns. And those, in turn, impart an anomaly into the SST field. And that is manifest as a PDO signal sometime. The decade-to-decade variability, we think, is likely driven by changes in the West Pacific Ocean currents, but they're not reliably predictable. So there's a certain sense of randomness here. And so the key here, and I mentioned this cautionary tale, is that the PDO is largely forced by ENSO and by the PNA pattern to be a shorthand for all of this variability that's going on over the North Pacific. And so we think about something like, well, does the PDO have an impact on North American climate? Well, the answer in wintertime, from a modal perspective, is probably not really. There are some interesting ramifications in the summertime where extratropical SSTs can play a more physical role as driving climate variability. But in the wintertime, it tends to have a much smaller role. And so this is kind of this cautionary tale for understanding that any kind of pattern, any single index, can be a combination of physical modes that makes it challenging to use by itself in an attribution context. So this is presented just to show how the value of teleconnections and being able to distill complex climate variability into these building blocks that we can use to reconstruct the climate and to reconstruct climate events, or to reconstruct the probability that extreme weather events occur in that context. While it's important, it's necessary, but it's not sufficient in the sense that we need to understand what's underpinning them, or else we can get caught thinking we know what's driving our climate, what's driving our change in weather from week to week, month to month, but really be looking at something that's less predictable than we think. And so that's the danger there. All right, so wrapping up here, I know we're coming up on time. I want to leave some time for questions. And hopefully Jenna will let us go over a little bit if we have some good questions here. So some conclusions: there are distinct and predictable low frequency variations. They're strong enough to affect our patterns and statistics of daily weather. And so the amalgamation of daily weather gives us climate, and sometimes the effect can be seen even at the individual event level. That's important. There are 4 well-defined classes of physical modes we talked about: long-term trends, ENSO, interannual, year-to-year tropical variability, intraseasonal or week-to-week tropical variability, as well as these internal patterns to the extratropics. The caveat there is adding into that fourth category, these internal patterns, these internal modes of variability. There is a lot of work to understand the relationship between those and stratospheric variability and those and other potential boundary conditions to the atmospheric system. So understanding that kind of sea, ice to land interaction as a potential boundary condition that could explain and provide some prediction skill at extended leads. Those are ongoing areas of research and work. Important takeaway: patterns are not the same as physical modes, and that's the whole point of that PDO cautionary tale. But we can construct analysis frameworks in which these converge. And so that's what I was saying in terms of highlighting a little bit of the differences between the 1987 analysis and the 2015 analysis. Is that the 2015 analysis uses a slightly different analysis framework by looking at an upper level height field where we have tropical, extratropical variability on a more even footing, and that framework we're able to distinguish a little bit between something like ENSO-related variability and what's going on in the extratropics. The NAO is really important. Strong impacts over North America are limited to the east, And so it's only really predictable on NWP timescales for sure, but we are continuing to monitor and to incorporate the latest research that suggests there might be some predictability from subseasonal external forcing. And actually that statement can also be extended. Perhaps there's some predictability even on seasonal timescales. The NAO and the AO are strongly correlated, so these really shouldn't be thought of as independent patterns by any stretch in your analysis or communication of these situations. And then, like I said here, that PDO is a pattern, not a single physical node. And so it's important extending that analysis to other patterns of variability like the NAO or the PNA is also possible. And so it just kind of makes sure that we're cautious about what we say we can attribute to a teleconnection pattern from a physical perspective. All right, looking ahead to part 2. So we'll do this in about a month. So we'll dig into teleconnections arising from particular and predictable forcing mechanisms. So we'll talk explicitly about ENSO teleconnections, what they are, what they look like. We'll talk about MJO teleconnections, and we'll talk about stratospheric-tropospheric coupling, which itself will kind of be a teaser for the November webinar on stratospheric-tropospheric interaction. I will also look a little bit of a case study. We'll use the winter 2013-14 as a great case of the prominence of the North Pacific Oscillation West Pacific pattern and its importance to the seasonal climate. We'll talk about providing climate context to the observed anomalies and show how we can use teleconnection analysis to answer questions about proximate causes of what we observe, or how we can use it to rule others out. And then lastly, we are going to I'll do a little bit more on some tools, resources, recent advances to better understand and help communicate the climate context that we are provided by teleconnections, how they can help us explain climate anomalies that we observe, and how in some cases they can even help us better understand the context in which extreme weather events can occur or have occurred. Okay, and so with that, I will turn it back to Jenna, who can take us through some questions.
All right, great. Thanks, Steve. Hi, everyone. This is Jenna Myers from Climate Services Branch. So there's lots of good information here. Thank you, Steve. And then a nice teed up for next month's part 2. If you have a question, just enter it into the chat box. So far, I have about 2 questions in here, Steve, so I'll go through them, and then hopefully, I guess we can hang on for a little bit if other people are hanging on, if we get some more questions. But here's your first one up, Steve. Given the limitations of teleconnections, do you think the best approach is to focus on using teleconnections to better understand outlooks versus using teleconnections as part of messaging to partners?
All right, great question. Thanks. So interesting. I wouldn't necessarily think of these as either ors. But yes, teleconnections are very useful potentially to understanding and attributing existing forecast and forecast anomalies. But likewise, a lot of people, and this is where the partners question comes in, I think is relevant, is using teleconnections when we're messaging. A lot of stakeholders, and I found this to be true in my engagement with stakeholders at CPC on teleconnections and seasonal, subseasonal outlooks in general, is that it does help us to construct the narrative and to message what we understand about the climate system. So there's a lot of things we don't know. There's a lot of things we just can't predict and won't be able to predict. But there are a lot of things we know, and there are some of these kind of known unknowns, and understanding what's important about these teleconnection patterns and our limitations to understanding and their limited predictability in some cases. And so showing examples, for instance, of when we have, El Nino is a great source of prediction skill. But when you combine an El Nino with a predominantly negative NAO during the winter versus combining it with a predominantly positive NAO in the winter, you'll see a dramatic difference in the surface climate. You'll see commonalities because of the common ENSO forcing, but you'll see how imparting that with a known pattern of variability in the extratropics can lead to this rich diversity of potential solutions. And so it helps to better, I think, can be a tool that can be used to help partners understand kind of the sources of these uncertainties, right? Here's what this looks like in a positive NAO framework and a negative NAO framework. And at this lead, that's where our uncertainty is, because we don't know for the season necessarily how this will work. Now, in the future, as we start to incorporate all of the great science that's going on in the around the industry, in the field in general, we might be able to get some clues as to, or some small shifts in the distribution toward an NAO phase, for instance, for a season. And that can be used to, again, further explain what we know, what we don't know about the upcoming season. So I think both are important, and I think maybe important for different reasons. So the first part is it helps the forecaster understand the context of the forecast, understand, kind of reconstruct the forecast, if you will, and then attribute the forecast to these building blocks, which is what teleconnections fundamentally are for us. And then likewise, it can also be really useful messaging to partners, because the partner, I think, will appreciate and understand this appreciate understanding and communication of what some of these kind of basic patterns are, how they generate the climate anomalies we observe, and which ones of them are more or less predictable, so something like ENSO is quite predictable, and how those all combine to give us the uncertainty that we have. So I think it's a great question, and I think the answer is both, but for different reasons. So hopefully that helps.
Okay, great. Thanks, Steve. I have another one that just came in from the field. I actually chatted it to you in the box so you can read it while I talk, because it is a little long, so just bear with me. How can we explain the anomalous warm 500 millibar storm track ridge pattern of 2020 to summer 2021 in the North Pacific the past 2 years, leading to back-to-back severe drought downstream in California? Can we label it on the PNA or another teleconnection? It has resulted in anomalous SST warm blobs in the Pacific.
Great, another great question. So I can't speak this specific case, this particular case study, off the top of my head. But in general, the question is fairly asked, and yes, we can look at the evolution of these patterns over the North Pacific, and we can see in analysis framework which teleconnection patterns were being flexed at the time. To what extent were they related to, for instance, ENSO, if any, during that period, or MJO forcing, perhaps, as well. And then we can, of course, see those footprints, and we can, in a kind of a linear fashion, you can rebuild, if you will, those SST warm blobs that resulted, and see which of these teleconnection patterns were flexing the most, and from there, which one of those would have been more or less predictable. That's also part of it as well. We want to understand, is this, if we have a flexing, for instance, of the North Pacific Oscillation WP pattern, like we saw in the winter 2013-14 and some extent 14-15, in that framework, it's unlikely that would have been generally predictable, but a small portion of it could have been predictable. And so it's in that context that we can really communicate what we understand about it. So yeah, in this case, I think it's a great question. I think it's a very appropriate question for teleconnection analysis to get our heads around. And when we combine that with other types of analysis, like modeling analysis, that can help us attribute this to different sea surface temperatures, for instance, or to try to help us bring us back to that physical underpinning. It's one thing. The numerical models are really helpful for wrapping our heads around the physical basis for the anomalies that we're observing in the climate system. And so I think, yes, I can't speak to a specific question, but this is exactly the type of question that's useful, that teleconnection analysis can be very useful for, especially in conjunction with other types of attribution analysis that we have.
Okay, great. Thanks, Steve. I'm going to hold on the last question that came from Andrea till the next one, part 2, because she said it applies for that one as well, so we're going to hold. Okay. I just sent in all the audience a link to the seminar series. That's where you can access the recordings as well as register for upcoming seminars. It's a Google Doc. Click on it there. And then Andrea or Ray, did you guys have any last minute thoughts? Otherwise, I'm going to end the webinar shortly. But thank you so much, Steve.
No, nothing on my end. Just want to thank Steve for his efforts today, and also for advertising the presentation coming next month and the month after that.
All right, guys. Well, thank you guys again. Thank you, Steve, and you guys have a great day, and we will see you next month. I'm going to end the webinar now, and the recording will be posted on the seminar series list website. All right, thanks, guys.